start off easy, and then we'll kind of ramp up in difficulty. Let's calculate the lim as x approaches 5 of x squared minus 3x minus 10 over x minus 5. Cool. Now, what type of function is this? This is a rational function, right? A ratio of two polynomials. Now, this is meant to be a pretty easy example. In fact, this looks a lot like the example we did last time in lecture, right? A ratio of kind of this quadratic and a linear factor. But now let's kind of examine it a little bit more precisely in terms of this direct substitution property. So direct substitution, I'll usually use ds to abbreviate that, direct substitution of x equals 5. And I'm doing as x approaches 5. So if I substitute that number, I just get, obviously, let's see, just a little bit of arithmetic gives us 0 over 0. Now, there's a few things I want to say about 0 over 0 first. There are two things that this kind of should scream out at you. Now, 0 over 0 is undefined, right? I mean, you can never divide by 0. So although 0 over 0 is undefined, what does that mean? What does that mean about the limit? It does not mean that the limit does not exist, right? I see this a lot from students. They'll say, oh, if I plug in 0, I get division by 0. Therefore, the limit doesn't exist, right? That's not true. All that actually means is that you are not able to plug in 0. You are not able to plug in that number to figure out the limit, right? It just means you have to figure out some other way of doing the limit, okay? So I'm going to write, although 0 over 0 is undefined, this does not necessarily mean the limit doesn't exist. Right, exactly. You can have a hole in the graph, right? Like Pranav says, you can have what's called a removable discontinuity, which we'll discuss on Tuesday, that exact term, removable discontinuity. But you can have a hole in the graph, right? This does not necessarily mean the limit doesn't exist. And there's a second thing, and I don't think we'll kind of appreciate the second point until a couple more lectures, because in the next few lectures, we're going to come up with different ways of computing certain limits. And the strategy that we choose for computing certain limits depends on the exact form we get when we directly substitute. So we could get 0 over 0, we could get 3 over 0, right? Depending on what you get, you choose a different strategy. 0 over 0 indicates to you a very specific but also very vague strategy. I will just say 0 over 0 suggests to you that there is algebraic cancellation. We'll say later different other forms might suggest something else. Like for instance, if I were to plug in 0 and I get 3 over 0, that suggests a vertical asymptote, but we would get to that in a later lecture. Okay, so let's see how we actually would compute this limit. All right, so let's be very careful and see and kind of explain why each of our steps is justified. We did this last time, right, in the last lecture. So first of all, I can just factor out the top, right? I can factor it as x minus 5, x plus 2. Nice and easy. That's always okay, because we can always factor something. Factoring doesn't do anything to the problem, right? It just essentially rewrites it in a different form. So factoring is always okay. But now what we want to do is we want to say, aha, x minus 5's cancel out. And we discussed this last time. Wait, in the last lecture, we discussed that this, you do have to be a little bit careful here. There's a subtle point that must be made. Recall that it is not true. These two things are not equal to each other, right? x squared minus 3x minus 10 over x minus 5 is not equal to x plus 2. All right, why? What if x equals 5? Right, the left-hand side of the equation is undefined, but the right side of the equation is equal to 7. But here's a question that we did answer last time. So even though these two things are not equal to each other, why is it still okay, nevertheless, in my limit to cancel the common factors and say, okay, these two limits are actually equal to each other? Why is it that putting the limit symbol on these two expressions suddenly does make them equal to each other?
Because it's not necessarily showing a value, it's just showing what sort of number it's going to.
Okay, so first of all, I want to make clear that this limit is a number. A limit is a value, right? A limit is a number. A limit doesn't approach anything. It might be that x is approaching something, or the values of x plus 2 are approaching something. But the limit is actually a number. And so CJ is on the right track. Does someone kind of want to jump in on that and maybe clarify that a little bit? Why is it okay for me to say that these two things are equal, even though these two things are not equal down here?
Isn't it like because the x minus 5 part, like it just doesn't satisfy the limit, so you just try to cancel out so you don't get 0 over 0?
Okay,
so
what does it mean? What does Angelica mean when she says the x minus 5 doesn't satisfy the limit?
You're getting rid of
Don't you actually like not care
Brandon?
about like the
Or
actual?
who's
Don't you?
talking?
Me. I know.
Emily. Okay.
Yes.
Emily.
Okay.
Don't you
We'll get
actually
Brent
not
next time.
care about the like the actual value at 5?
Okay, good. Right. So it looks like everyone kind of got it, and we kind of built on it. And so that's, I would say, the precise reason, right? The limit symbol tells you you do not care about what's happening at x equals 5. So you're allowed to assume that x is not equal to 5. I apologize to Bryn or Daphne, who is also trying to speak. Sometimes this is how Zoom goes, right? You're all trying to talk over each other. Okay, so this limit symbol, the limit symbol tells us x is not equal to 5. So cancellation is okay. All right. And now what do I do? Well, now, okay, now forget about all this. Like, who cares? Right? Because we've kind of determined that what? I only need to calculate this limit at the very end. But what is the limit of x plus 2? Well, x plus 2 is a polynomial. And polynomials have this property that you can just plug in the number and that's it, you're done. So that's exactly what we're going to do here. We're just going to plug in the number. We plug in 5 and we get what? 5 plus 2 is 7. So right here, I am using the direct substitution property, DSP. All right, okay. So the algebra was not meant to be difficult in that problem. Right? It was meant to be pretty, simple. But we want to make sure that all of these little notes I'm writing in orange, these little subtle points, make sure you understand that, right? Make sure you understand that the limit symbol tells you x is not equal to 5. So that means the cancellation's okay. Why'd you find 7? That's literally, Pranav, just substituting in x equals 5. 5 plus 2 equals 7, right? DSP, direct substitution property. I understand, but why? Well, I can't prove that to you. It's a little bit beyond the scope of the course. I mean, you might ask, why do polynomials have that property? It might seem obvious, but why do they have that property? That needs tools that are beyond the scope of this course to prove to you why do these functions have that direct substitution property. So it's a good question, but unfortunately, I just can't answer it in this course. It'd be more for like an analysis course, like proving polynomials really do have that property. Again, I think it's an obvious